Okay, so this class here is going to wrap up our exploration into circular functions, looking at the applications of circular functions. So we've all seen questions where you're given some generic version of your function and you have to use further information provided to essentially fill in those blanks. That's one of the more common parts of doing your applications of circular functions, where you'll have to create the rule that you'll be using, create the function using the information provided, and then analyze it in some way, shape, or form later. So let's have a look. So the first part we'll have a look at will be how do you actually create that rule. It's going to borrow a few things from what you'd already be used to when solving for like polynomial stuff, for instance, using basically trying to convert the worded or perhaps even graphical information that's provided to you into what term that would actually relate to, whether it's the amplitude, kind of the period, the end term there, or your translation terms, essentially. There's no real set order that you have to solve each of those terms in. It's more so, I've outlined them in that order specifically more so because that seems to be the order in which things are most easily solved. Not necessarily the case that you can't do step 2 and then step 1, but it's often the case that this is sort of the natural flow of when that information is most readily available. So let's have a look. So we've got a fully worded statement here. There's no actual, there are numerical values, but it's not like saying amplitude equals something or whatever. We have to sort of infer what each of those means in our scenario. For the purposes of this, I'll follow the framework that I have outlined here, but again, like all of these sentences that have a numerical value attached to them could more or less be done in any order with a few exceptions. But okay, first, if you can identify the period in the scenario, then that'll allow you to solve for n, because the period of your circular function is always given by 2 pi divided by n. I don't think I've ever seen tan used in an application before. It's a fairly weird graph that wouldn't really describe too much in the real world. Whereas things like your sine and cos circular functions, you'll often find those are things related to anything that is cyclical in nature, whether it's like your high tide, low tide, going around a clock, anything circular motion in that way. Circular functions can be used to describe that sort of thing. So, when calculating period, we use the 2 pi divided by n equation because that's the one that is relevant to sine and cos. As for how you actually get the terms involved in there, well, the period is always just the time in which it takes for whatever the scenario is to repeat once. And there's a statement here that tells us something related to that. The time between high tides is 12 hours. So basically you go from high tide to low tide, back to high tide. That is a duration of 12 hours. So the period, capital T, should therefore be 12. It's the time in which it takes for the tides to cycle, go for a full cycle. So if capital T is 12, then 12 is equal to 2 pi divided by n. N is now the only coefficient left in there, and sure enough, we can just sort of rearrange to get n back on its own. N is going to be pi over 6 in this case. And so that's going to go right there. Any questions so far as to how we've gone from written information to equation? Next up, we'll have a look for the vertical translation. Sometimes it'll be given to you directly, other times you might have to calculate it. So we would know from, I don't actually have a picture of a graph here. Let me see if I can find one. We know from our circular functions that the vertical translation of it is essentially the mid-level of that circular function. So this one here is looking to be, what, 3.5-ish, wherever the midline of that is. So sometimes you'll be told the middle tide maybe would be 3.5. Maybe you'll be told the values of the high tide and the low tide, and then just sort of have to calculate the midpoint to get there, which is the case here. So in the framework I've mentioned, you might be able to be told it, or you can calculate it via just doing the midpoint of the peak and trough. Oh, wait, never mind. We do actually have it here. The average depth of the water is 5 meters. So we had the average and the high tide. Average in the context of circular functions is going to mean what I meant before, the middle line, the midpoint. So that one's actually already there for us if you needed to. So our vertical translation is going to be 5. I've written b equals 5 rather than c equals 5 simply because that's the term that's written in the question itself, right? They're using all these different terms in there. That is question specific. We would normally think of vertical translations as a C term, but that's just sort of whatever. This is just generic notation. This is the question-specific terms that we're solving for. Like let's say, for instance, that was the low tide value instead. You could just do high tide plus low tide divided by 2, and that would get you the average, or the middle of those. That gets us our vertical translation. Next up from here, we can start calculating the amplitude. There's a few ways you can go about it if you don't already have it. You can either look at the peak and then subtract the middle level, or you can look at the trough and subtract that from the middle level. It's basically the difference of saying, okay, I have this and I have the middle. What's the difference between those? Or I have the middle and I have the bottom. What's the difference between those? Technically speaking, amplitude should always be positive, but the A term itself is not necessarily exactly the amplitude. There's a bit of a nuance there where technically you could go either way, depending on which way you do this. You don't really have to worry about it though, because so long as your circular function has some horizontal translation in there, it doesn't matter whether you have a positive or negative here. It'll just change what goes in that spot. And if there's no further information in the question that would contradict which one of these you would use, then both options are going to end up being valid. So all I want to highlight there is, both of these will give, one will give a positive, one will give a negative. Just don't worry too much about which one you should go for, because this will end up fixing itself for you, which we'll see in a moment. So in this case, the information we had was, as we said before, the high value and the middle value. So you just find the difference of those to get the amplitude, because by definition, the amplitude is the distance between the middle and the peak of the circular function. That gets us our A value of 3, or you could write -3, it won't matter. Then, once you've got all those terms, that's why I'll usually use the horizontal translation last, because once you solve everything else, what you can essentially do is sub in some known point into what you have, and then whatever comes out of that will sort of fix any, they're not mistakes, they're just compensating for any values you've calculated earlier. So let's recap. So currently we have found our n value, pi/6. It's going to go in there. We have found our capital A value, 3. That's going to go there. And we have our B value of 5. That's going to go there. Only thing left is your h of t, your t, and your epsilon, that little e looking symbol there. So this is where knowing what your circular function is actually trying to describe matters a lot. This is the function h of t. For those who are more used to these kinds of application questions, you might recognize that as like height with respect to time. As far as where you would figure that out otherwise, you've got this statement here. Assume the depth of water, h of t. So h of t is the depth of water. Depth, height, more or less the same thing. Depth of water is h of t, and t is a number of hours, so time. This definition specifically being number of hours after noon does matter quite a bit, knowing that it's specifically after noon, because when it comes to subbing in a known point to solve this horizontal translation, there isn't a whole lot here that tells us a known point without understanding this definition here specifically. Because, we're told period information, sure. We're told some y values, but we're not told like time values at which those heights occur. But there is a statement here. At noon, there is a high tide. So this is a time value with respect to a height value. Time is noon, and so therefore that would be t equals 0, 0 hours after noon. And high tide, well, that would mean h of t would be 8. So you'd put an 8 here, you'd put a 0 there, and then whatever's left over, you're now going to wrap around and solve for epsilon, the horizontal translation in this case, or kind of the horizontal translation. Yeah, that means high tide, so we sub in our t equals 0, our h equals 8, and we can see that after a bit of simplification, there's only one variable left. All we're going to do now is solve for that value. What you'll notice a lot of the time is it'll simplify into something fairly repeatable across different questions. Like for instance, if you were to do any of these kinds of questions where you're trying to solve for the rule, a lot of the time you'll get sine equals 1, sine equals -1, sine equals 0. You'll get very fundamental things that exist on the unit circle. Before I go any further, anyone familiar with the unit circle? Why do you reckon we got sine equals 1 in this case? What was it about the point we used that might indicate sine equals 1? You know, beyond the algebra, of course. I'm also interested to see if anyone knows like why the algebra, or at least without having done the algebra, why you might assume it would map to sine equals 1. Bit of a tricky question, but maybe something to consider for investigation type SACs. To do with the statement that I've highlighted there, that being the point we subbed in. At noon, there is a high tide. Think about the range of sine as well.
Sine can only go up to 1.
Yeah, so that's its absolute maximum value. So when you sub in the peak in this scenario, after all the algebra simplified, you would get back to the highest possible value that could be on the unit circle, which is 1. Nice, I'm glad you actually spotted that. That's good. But cool, okay. So we're looking for a peak. Sure enough, it's going to be for sine equals 1. Just to make sure everyone's on the same page, I'll pull up the unit circle to see where we go from here. Okay. So we're doing sine equals 1, which means we're looking for where are the y values equal to 1. There's only one spot on the unit circle where a y coordinate is equal to 1, and that's at this angle pi over 2. Technically speaking, if you really wanted to, you could go multiple times around the unit circle. There's no need to, don't bother, but it is valid to technically do that. Just choose the most and easiest one available there. So you're going to get epsilon equals pi over 2, and that's going to be your final answer, at least for this scenario here. There is a nuance we'll touch on just briefly, but before I do that, is there any questions or clarifications to make here so far? This one was fairly straightforward in the sense of like what it wanted out of you. It wanted you to solve each of these terms and then give the rule of the circular function. If there wasn't a rule provided here, and it just said find a cosine or find a sine, or maybe even a follow-up question, it'll say something to the effect of convert to a cosine. This is where you can start using your circular function properties, trig identities, symmetries of the unit circle, however you want to think about them, to flip between different things. One of which that you could potentially be using would be this one here, the fact that when sine x plus pi over 2, when you have pi over 2 as an addition onto sine, it can become cos. All that to really highlight that this is functionally identical to this. These mean the exact same thing. We're using this one because that's what the question requested. If a follow-up question then requested it to be a cosine, you would do something like this to get it there. I've never seen a follow-up that's asked you to change whether you're using sine or cos, but I thought it was worth pointing out that there are multiple ways of describing the exact same circular function. It's one of the weirder functions where because of its periodic nature, you can do weird things like this. So far, that's all been about the creation of circular functions. Okay, recap. Sure, let's do a recap. I'll do a brief recap and then we'll go into a bit more detail when we actually just sort of go through a live example, and hopefully that'll be more enlightening. So basically what we're doing so far was going through how you can solve the rule for a circular function, and I provided a framework here. You don't necessarily need to do them in this order. It's more so about this is typically when the information is most available. If you follow this sort of procedure, you'll get most out of what you're looking for. And we were just sort of going into detail as to how you can convert these worded statements into actual equations that you can then solve for unknowns. It's got some similarities to solving like polynomials, for instance. I think it'll make most sense if we just go through another example live together. So I won't do that one because, well, we'll recognize that one a lot. This one, a little bit different. It's got a graph involved, but it's still the same idea. This will be a bit easier actually because you can see the numerical values directly attached to them. Let's see if we can work through this. I'm going to do question 1. The graph is provided there, so there's no like written statements, but we do have the numerical stuff to work off of. And we'll just go top to bottom, basically calculating everything we need to until eventually getting our rule. Let's have a think. First up, we've got to get the amplitude. In this case, how do we calculate amplitude?
Three, like the distance from the lowest kind of point to the highest point the graph reaches.
Okay, definition's a little bit different than lowest to highest. It's similar to lowest to highest, but there's a different bound that we're looking for there.
We can take the difference between the maximum and minimum and then divide it by 2.
That'll get you the middle of it, not necessarily amplitude. Amplitude by definition is the distance from the peak to the middle. So it'll be like from that dotted line to the peak. That's amplitude specifically. So the first example would have been the range, where you go from bottom to top. That would give you the range of the function. The next suggestion there would have got you the middle, exactly, adding these two and then dividing by 2. Like that'll get you, well, none of them are listed here, but you need it anyway. That'll get you the plus c. For amplitude specifically, we want to find the middle and then the peak. So we will need to find the middle anyway to get there. So how are we going to get that middle again?
Wouldn't getting the difference between them and dividing by 2 get the amplitude, because like that's the middle. Okay, so 5 minus 2, that's the difference, and then divided by 2, that's 1.5. Isn't that the amplitude?
Yeah, actually that's right. I might have either misheard you or just not saw that. I might have just in my mind thought it was finding the middle, which technically you are finding the middle, but yeah, then you're dividing it by 2 afterwards. Yeah, no, that works actually. Nice. Sweet. Let's do it that way. So you do the 5 minus 2 to get to the 3, and then dividing that by 2. That's kind of cool. I never would have done it that way, but it works. Sick. Well done. But okay, that gives us amplitude. Next up, asking for period there. Reminder, period is the time which it takes for the circular function to repeat once. And analyze that graphically.
It repeats every 12 hours.
Here is going to be 12 hours. Yep. That's it. Yeah, you'd want to probably put hours here because now we're going into what is it? We're going into applications, so we want to start giving units for things. Yeah. Okay. Next up is going to be the rule for our distance equation. So you can see here they haven't actually suggested whether you should use sine or cos. You can use either and make it work. There's one that would be easiest if you choose, if you put a bit more thought into which one you should choose, but both will work perfectly fine here. Timothy, I don't recognize. When did we have a chat last, Timothy? Anyway, I'll follow that up later. Rule of DOT. So we can choose sine or cos. It won't ultimately matter which one. What should we start with?
Sorry, what was the question again?
So sine or cos, basically. It won't matter which one we use, but one is technically easier. So if you want to put some thought into which one would be ideal, then that's fine. But otherwise, I can just choose whatever. As for what this is, it's going to be the Unit 3-4 book, by the way.
Okay, so the sine comes out from the origin. So I think if you use sine, you'd have to just like apply translation just to move it up.
Yep.
Is that correct for sine?
Yeah, sine comes from the origin,
Yep.
starting.
Yep. Yep. So would it make sense, like if you did sine, you just do the translation, or does it really matter?
It won't matter in the end of the day which one you choose. I'm just curious to see like your thoughts around what one you might choose, because what we discussed here was like right at the very bottom, like here's one way of doing it, here's another way of doing it, and they look vastly different, right? Like here's a sine that has a translation in there, here's a cos with no translation in there. I'm just curious to hear like, what kinds of things you might think about to choose. Ultimately, you can choose whatever, though both can work.
Yeah.
So yeah, sine, right? Both of them are going to need a vertical translation to get it up there, because both sine and cos are still going to be oscillating around the middle. As for the peaks and troughs involved, where they're located is going to be different depending on if it's sine or cos. And let's just do sine, just because why not? And we'll see in real time what we'll have to adapt to make it work. So y equals a sine n bracket x, or I guess I could use t here because we're using hours, t minus h plus c, something like that. Some of those terms we have already, like the a value, or at least that's technically amplitude. Reminder that amplitude is always positive, but the capital A may or may not end up being positive. 3/2 sine n bracket t minus h plus c. Cool, okay. Anything else we can start either solving for or calculating? Or even if we also have some information left there, actually. N, we've got H, we've got C. Two of those are quickly either solvable or we've already found them. Okay. Let's just go left to right then. So N, what is that usually related to when it comes to our circular functions? What kind of equations does it belong to? What kind of, terms does it usually describe? What's that usually related to?
Could you repeat your question? I didn't get you.
the n value here. So we're just going to go left to right on the terms that are left to solve. What's the n value usually like related to? Do we know any equations? Do we know what it usually is there to? What's it usually there to do?
The period.
Yeah, directly related to the period, right? We know the period, but that doesn't necessarily mean we know n as 12. We just know the period is 12. How can we now use that to get n?
We do 2 pi divided by
Mhm.
the period.
2 pi divided by n, yeah. So period is 12, and period is also 2 pi divided by n. Therefore, 12 equals 2 pi divided by n. 12 equals 2 pi divided by n. N equals 2 pi on 12, or pi on 6. Nice. So that gets us another term. Y equals 3 on 2 sine pi on 6 bracket t minus h plus c. Cool. Okay. T doesn't really count as a variable. Next up would be h. H will typically do last. If we remember from the framework that I provided, you would want to do your horizontal translations last. Typically because you'll usually do that by subbing in a known point at the very end once everything else is solved. So that leaves C. What is C usually when it comes to our graph or any other application?
Vertical translation.
There we go. Nice. Everyone loves that one. Vertical translation, that's right. What's our vertical translation? Do we remember? You've got the picture on the screen share as well, or you've got the calculations we did? Most of the calculations we did.
C will be 3.
3. 3, 5. Not quite. C's got to be the middle of that. Because if you had 3 in the middle, you've got 2 up to 5, and you've got 1 down to 2.
So is it 3.5?
Yeah, 3.5. That's better. So midpoint calculation, you take your peak, you take your trough. Yeah, and then you halve it. Always remember vertical translation with plus C from calc. From calculus? Oh, right, okay, yeah, the plus C from integration. Yeah, no, I know what you mean. Yeah, gotcha. Yeah, so 3.5 there. Y equals 3 on 2 sine pi on 6 bracket t minus h plus 3.5. Now, we technically have a decision to make here. I do have a horizontal translation term in here. Alternatively, we can fix something else, or change something else rather, about the function to not need to solve that. If we have a look at the picture itself, oh yeah, go ahead.
Can we use cos instead? Negative cos?
Yeah, negative. Okay, is it gonna... Let me just double check to make sure that flipping to cos won't break it. Nothing in here was sine or cos dependent, so yeah, choosing negative cos. Because if we have a look at the picture that we have, if you imagine what negative cos would do, regular positive cos starts at a peak in the t equals 0 spot. This one obviously now starts at a trough. So choosing negative cos would actually get us to stay there exactly without the need to solve for horizontal translation. So yeah, choosing to write negative cos instead would set our horizontal translation term to 0. Or in other words, just not need to solve it. So negative 3 on 2, writing cos instead pi on 6t because the h is 0, and then finally plus 3.5. What's the difference between the t variable of 12 hours and the one in the equation? The one in the equation. Oh, little t. Little t is time, capital T is period. That's just a term definition there. So capital T is the 2 pi divided by n, the period calculation. Little t is time. Both of them have units of time, but little t is like you know how you have like f of x? It's the time variable, the thing that changes over time, versus the period. That's the fixed distance from peak to peak or trough to trough. Does that clarify that? Let me know if not. Otherwise, if we don't spot being able to convert to cos, we can still make this work. We just need to now solve for h, or whatever h value would work in this scenario. Solving for h is a matter of subbing in a known point on the graph. We have a couple that we can choose from. Any suggestions? What kind of point could we shove into that function? What's the h variable again? H is here, the horizontal translation term. So because if we have a look at everything we have our y value, we have our t value, we have our h. Those are the only variables left. So if you want to now solve for h, if you can shove in a time and a, well, I guess it should say d of t, realistically. You get it now, the time variable is kind of the x. Yes, basically, exactly. So you got your x on y-axis. Our y-axis is distances, and our x-axis is time in hours. Which, you know, means I probably should have been this whole time using d over here. Or even more specifically, d of t. But yeah, we're just going to sub in a point. Doesn't matter which one you pick. Probably the easiest recognizable one would be the 0, the 2, right? So time equals 0 when distance equals 2. You could pick time 12, distance 2, or even 24, distance 2. Those are kind of the only ones that have direct markers attached to them. Yeah, nice. And the minus h is directly attached to t, meaning it's horizontal. Yes, that's right. Yes, the h. I'm using the same sort of terms you would see in like your polynomials, for instance. So the h would be, yeah, the horizontal translation. You're right. But yeah, as far as continuing on the question, we'll sub in t equals 0 and distance equals 2, just because that's, you know, smallest numbers. So distance 2 minus 3 on 2. Oh, sorry, we won't do cos. We'll do the sine one because that's the one that actually has something to solve. Sine pi on 6. T is 0, so you're literally just left with the minus h. And the 3.5 will rewrite with fractions. Yeah, and then we just start solving. So we've got the 2 minus 7 on 2, so let's just fix that up. So it'll be 4 on 2, 7 on 2, sine negative pi on 6h. Where is the minus h in the bottom? D. Oh, yeah, in here. What we were describing there was you can more strategically pick whether you use sine or cos, dependent on what you see in the picture or otherwise in the information you have provided to you. So what you'll notice there is the change that we did was flipping from sine to cos and then making the amplitude negative to compensate for that. Because if you think about what cos does, we have a look at our basic graph. That's our basic cos. Cos normally starts at a peak. If we look at where our graph starts, it starts at a trough. If you have a look back at the screen share of the picture that we had provided there. And so what you can then do is say, well, okay, if I wanted to start at a trough instead, I can now do negative cos, which would do something like that. and then all you do is you vertically translate that up by the same amount, because vertical translations work the same way for cosine sine, thus putting the trough at the time t equals 0 spot that you want it to, without needing to find a horizontal translation. So that was a more advanced way of doing things, seeing things ahead of time, seeing what you can do to simplify how much effort you put in. What we're covering now is, for whatever reason, you don't see it, right? And you're just like, cool, I got my H term, let's just go straight from there and solve that way instead, because for whatever reason you don't see the strategy on the day. Clear enough the differences there? Yeah, matter of intuition, exactly. Okay, cool, so that's that. And then all we're doing here is, well, failing to drop things out apparently. Here we go. 4, 6, 7, so minus 3 on 2 divided by 3 on 2 is going to get you minus 1. Minus 1 equals sine. Again, what we saw before, you're either going to get like a peak or a trough. You know, the absolute minimum value of sine being -1 on the unit circle, because we subbed in a trough. As for where that is, unit circle, y value of -1 is down here. That's going to be the 3 pi on 2 spot. Or if you wanted to use even smaller values, you could use -pi/2 if you wanted to. Any iteration of going around the unit circle will work for that. Just because I've already got a negative in here, I think I'll do the -pi/2 just so things cancel out. So essentially, this thing in here is the same as that. Minus pi on 6 h is equal to minus pi on 2. The negatives and the pi's are going to cancel, cross multiply, 2h equals 6, h equals 3. So when all is said and done, if you were to do it that way, using the sine, you would have, okay, 3 on 2 sine, pi on 6, t minus 3. That's minus 3 because we had minus h. So if h is 3, we have minus 3. And then the 3.5. Typically, if you're using fractions, try not to intermingle them with decimals. If you use fractions in one spot, use fractions in everything else. If you're using decimals, use decimals all over. That's about it, really, in a blurry way. There we go. How did you come to 2h equals 6? Yeah, so that was I did a fair few things in one go there. Noticing negative pi was common to both terms. You can cancel them out, divide both sides by negative pi. And then cross multiplication. So times both sides by 2, times both sides by 6. I'll do it in a bit more detail. So, if you cancel these out, you would now have 1 over 6h equals 1 over 2. Multiply both sides by 6. And, that's actually all we needed to do in that case. Just multiply both sides by 6 and you would have been fine. But I did a full cross multiplication. Okay. Any other questions as to how we got there? Have a question? Yeah, sure. Need a sec. Yeah, sure. Fair enough. Okay. While you're typing that out, I'll come back to you on it. The next question on the in the Cambridge book is to now figure out the length of the hour hand. So we didn't really talk about what this graph was describing, just that we had the graph. This graph is measuring the distance of the tip of the hour hand from a large clock to the ceiling. So basically, if I were to draw a quick picture of what that would look like, you have a clock, it has the hour hand, which kind of looks like the minute hand. Let's fix that. There you go, the hour hand. You have a ceiling, and our function d of t is measuring this distance here from the tip of the hour hand to the ceiling. So for instance, you might have another clock with an hour hand over here. distance d of t, in that case, is this distance here. That's the scenario. As for the question, when we were at y equals 3/2 sine, how did we decide to sub in 2 instead of y? That was me subbing in one of the points on the graph. So if you take a look back at the screen share, we've got a known point that we can see on the graph, 0, 2. And since 2 is our height, our y value, or distance, the 2 is going to replace the y there. Yep, cool. Okay, so now that we understand what this thing was actually depicting, the analysis of it is how do we now figure out the length of the hour hand based on the circular function or maybe other information that you have. Would you be able to say, what would you be able to do y as 5 if you wanted? Yeah, you could, but you'd have to be sort of guessing what your t value is. It is calculatable. T would be 6 in that case because it's going to be the center of your of that period. But it was, yeah, you can use literally any xy coordinate you see on that graph so long as you can reasonably use it. But okay, so based on the information we have so far, how might we figure out the length of the hour hand? Drawing these little pictures helps, I would say. Drawing the hour hand in different spots, looking at what happens as the distance either increases or decreases over time. Basically what you would see is if the hour hand is pointing directly up, the distance is minimized. It's as tall as it's possibly going to be. Whereas if the hour hand is pointing directly down, the distance is now maximized. It's as far away as it can possibly be. Then you've got everything in between, right? As it goes around the clock, distance gets bigger, 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 smaller, 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 smaller. There is one understanding that relationship will help you find the length of the hour hand. I'm curious if anyone can get it. And once you know this, you'll know it for every other application. Bit of a tough one. I'll pause for a while for you guys to think about it because knowing why is kind of important, or at least being able to do these sort of things in the SAC, because it might not be. This one's a fairly common one. They use this a lot, clock-related stuff, or things that move around in a circle a bunch of times. Other times it won't be as obvious, but they'll still ask similar questions. So I'll take a longer pause than I normally do for these. What was the question? So it's IV on the Cambridge book, the length of the hour hand.
Is the length of the hand going to be the amplitude?
Yeah. What gave you that conclusion?
Well, I just gave it the thought.
Say again?
I just gave it a thought.
Oh, just gave it a thought. Yeah.
Yeah.
Do you know? Is it just sort of like an intuitive feel for it, or do you have any could you put it in words? Why is the amplitude?
It's because the hour hand, the midpoint of the hour hand is, the middle, and the hour hand goes up and down. So yeah.
Yeah, so I'll try to highlight what you're describing there with a couple of key pictures. So basically what you're saying is, we have this graph. In fact, it'd be easier if you... Actually, yeah, let me draw it out here as well, just briefly. So we have there's your one cycle, there's our trough, there's our peak, and you got this middle bit, and you got these extremes and you got this middle bit here. So basically you got the middle as compared to the height of the ceiling. You've got the absolute bottom as compared to the height of the ceiling. And we've got the, when it points directly up, as compared to the height of the ceiling. Each of those is related to one of the key features of the graph, whether it's the trough, whether it's the peak, whether it's the middle. Because our y values are capturing distance here, this one is related to the peak, this one is related to the trough, and this one's related to the middle. And so if you notice that, what we see is the only difference there is the length of this hour hand. So the length of the hour hand is the thing that's creating our the amplitude there, basically. The distance between the middle versus the peak and the trough. Excellent, yeah. Once you see it, you'll never unsee that now. A lot of things will have a circle and a center point. It might not be a clock all the time, but very common that it'll be something like that you'll look at. Cool, that'll be the hardest part of this by far. Does that need any more clarification there as to why it's amplitude? Because everything else here is going to be just kind of whatever. The questions are more similar to your polynomials type stuff that we're already used to. Cool. Okay. Part B of the question, at what times is the distance less than 3.5 meters from the ceiling? Basically, this is similar to, it doesn't even matter if it's a circular function at this point anymore, right? The function could be literally anything and the question would still be solved the same way. At what times is distance less than 3.5 meters from ceiling? So I think, how would you normally solve that for polynomials, for instance, or just any other function? Circular functions is hard until you see a visit. Yeah, visual representation of this sort of stuff is really important, especially with like this question 4 thing here, particle moving along a straight line. That was the weirdest one to think about when I was studying. But yeah, drawing these pictures is helpful for sure. Anyway, part B. At what times is distance less than 3.5? Polynomials you just solve normally, disregarding the circ function requirements. Yeah, so what does solving this kind of question normally look like? If this was a polynomials question, what would you actually do? Even assuming you have calc, maybe.
You can find where it is, wherever it's equal to that.
Yeah.
And then look at the behavior of the graph and find the rest of it out.
Yeah, precisely.
Or we can use inequalities.
Yeah, inequalities. Inequalities will be tough for polynomials and circular functions as well. A lot of what we talked about with inequalities is that it's best to draw a graph and then just sort of look at it graphically. But yeah, all of what you described there is perfectly fine. Cas solve for function equals 3.5 because meters, we're talking distance, and distance is on our y-axis. So it's just y equals 3.5, solve for, in this case, time. This one is doable without a cas, simply because the value they chose, 3.5, is a value that we know already. It's the middle of the circular function. So as long as we understand how circular functions work, the middle, or I guess I should say basically, all key features of the graph are located at quarter period intervals of each other. So basically from 0 to 12, every quarter of that is a new key feature, a peak, a trough, or a middle. And so basically for 3.5, you're looking for where's all the middles. So that's going to be t equals 3, t equals 9, t equals 15, 15. I'm kind of just eyeballing them. Basically, quartering 12 into 3, and then each of those key features is 3 separated from each other. So you just label the middles. At least those will be the breakpoints. As you discussed, it is an inequality because you want to do less than that. So technically our answer therefore becomes from 0 to 3, from 9 to 15, and then whatever 21 to 24. You write all of those. Would question 1 work with a polynomial? Would it still be no? Well, yes and no. There is technically a way to approximate a circular function with a polynomial to the infinite power. What's it called? De Moivre's theorem? No, that's something different. Basically, you would have to have a very high degree polynomial to get it to do stuff like this. It will eventually break down because all polynomials have to either be at the extremities, they have to either have a quadratic type shape where basically, if I start drawing some examples, let's say, we have our approximation of a circular function here. At the extremities, it will either become quadratic in nature at the end, or, maybe I'll just do that again. It'll either become quadratic in nature or cubic in nature afterwards. And how long it takes to do that will depend on how many powers you have in your polynomial. Technically doable, but it'll always be an approximation, not an actual thing. That's more for like university level stuff. You'll never have to worry about this. Did I ever do special in school? No, and no, I don't do special tutoring. This is just for math methods specifically. Although in university, you basically end up doing a decent amount of special in your first year. Cool. All right. What else? Is there anything else? Questions like, when is the water 2 meters up the wall? This is for the for a different example in question 2. Again, distance on your y-axis, you sub in t equals 2 instead. What's the earliest time of day in which the water is at its highest? Well, highest would refer to peak, and so whatever the peak is in your scenario, you sub that in as your y value and solve for t. There's not too many nuances to talk about any further from here. Greatest distance, peak. Least distance, that's a bit of a weird phrasing, but that's going to be the trough. Times which it's 5 meters. Again, same thing as before. Weird thing here describing the motion of the particle. Yeah, we've got enough time to discuss this one. I don't think anyone's going to be able to get this themselves, but I might be surprised. Let's talk about it. A particle moves along a straight line. Its position is given by that circular function. We're not going to worry about any of this so far. In fact, to save some time, I'm going to cas out what that graph looks like, because the important thing is going to be on the analysis of it here. Describing the motion of the particle, what's actually happening. Let's have a think. So we've got 3 plus 2 sine 3x. That's our circular function. They didn't give a domain, so whatever. Question, if we don't answer this once finish. Yeah, sure. I'll do that shortly after we discuss this. Describing the motion of the particle. So this is a graph of x of t. Position is x. So whatever reason, x is on our y-axis. This is very common in physics type stuff. They'll put x as distance and they put it on the y-axis, and then time will usually be referred to as the x-axis thing. So on our y-axis here is the distance relative to some fixed origin.
Is the behavior going to be like back and forth?
It's going to be back and forth. Yes, it is. How do you know that?
Well, it's just a straight line, and
yeah,
the x-axis is time, right?
X-axis is time, correct? Yeah. So
Yeah, so
yeah, I mean you're
um
right, absolutely right. It says it's moving along a straight line, and so basically, well, with reference to some fixed point, right? So basically, we have a fixed point, the origin, and it never actually goes. Actually, here's something for you to try and touch on further. Based on the graph you see there, let's assume. Oh, I don't even want to say anything further. If you were to draw a kind of picture to describe this, I know it's kind of hard to dictate a picture. By convention, right is positive and left is negative in terms of distances. If you were to sort of describe where it is in relation to the origin, what kind of distances is it covering?
is it going to be covering, well, okay, if the origin is the midpoint, then it's only going to deviate as much as the amplitude.
So something like this?
Yeah.
Almost. So y-axis is x, the distance, relative to a fixed origin. All these distances are positive. So if by convention positive is right and negative is left, what you actually have is it's oscillating over here instead. This is really tough to get because the minimum distance from origin is 1 in this case. All right, so this distance here is 1. The maximum distance it can be was 5. 3 plus 2 gets you to 5. So it's actually oscillating around here with the origin. This is where understanding origin on a graph and origin as far as the scenario aren't. You got to treat them. They are the same, but they're as far as how you're depicting them in a picture, they are different. Origin is the fixed point by which you are describing with reference, whereas on the graph, actually, here's a better way of describing it. The graph has time and distance information in it. Time on the x-axis, distance on the y-axis. This graph only has distance-related stuff. It's all positional, right? Going left to right is positional. Going up, down, it's all positional. So because we're using purely positional-related stuff, what the origin means in that scenario is a little bit different. Is it clear enough why it's got to go oscillate to the right rather than equidistant from the middle? Because you got really far into that, which is really good. Like this, I don't think I ever got this in methods when I was studying, actually. But cool. If there's any further questions, feel free to stick around. Timothy, I do need to clarify a few things with you, just to make sure we're all on the same page. But otherwise, yeah, for the rest of us, feel free to enjoy the rest of your day.
Thank you. Have a good day.
Cheers. You too. Oh, right, the question. Feel free to answer this once we finish. Wondering if I'm going to the classroom content part by part.
Like what I meant
What's the
is like if I'm kind of like just going through the entirety of kind of like your syllabus, like has like you have like the subsections for each kind of like like subtopic. Is that a good way to revise? Just kind of like going through everything.
Going through the things that are relevant to where you're up to. I wouldn't go like start to finish, because this is more so matching like the order in the textbook. Your school might be doing different things.
I mean, yeah, my school's going pretty much off the textbook, so
it is. Yeah, okay.
Yeah.
Totally fine to do that.
Yeah.
Those lessons in there, those are like teaching you the fundamentals.
Yeah.
As far as practice goes, like the textbook, obviously you got to practice off of that, but it's more so if like you need to revise, then getting an idea of the content, sure.
Yeah. Do you have like, it's fine if you don't, like, I was wondering if you have like a list of like recommended questions for each part of the textbook, or?
For each, not necessarily. For each of the classes I've run, I drop those in.
Yeah, I'll probably look through the lesson recordings then.
Not on the lesson recordings. I've dropped them in here.
Oh, sorry.
So maybe I
Yeah.
should actually, in each of the lesson recordings, drop that. Yeah, actually, that's what I'll do. I'll drop them on the lesson recording things as well.
Yeah. Cool.
Easy. All right.
Awesome.
Thanks, mate.
Thank you, Chris. Bye.
Cheers.
Cool.
Timothy. So I was going through the list of people. Is this your name that you've joined under? I'm just trying to keep track of who's who. Yeah. Okay. Who was your parent? Because I've got Anya supposed to be with us. Monique and Nihal. I haven't got your name written down here. Not sure what's wrong. I'm on the Classroom website too. Classroom. Yeah, so the Classroom, that website. Let me suss that out. What was your last name? Alexander. I don't see a Timothy Alexander on the Classroom. It's really strange. Did you sign up under that name? I'm seeing a Timothy O'Hara. And that's it. You're on it right now. Yeah. If you click the top right corner and go to your profile, what does it say? I'm just trying to find your account. Because we've had people drop in, and I guess the link got like leaked or something. There was one guy who was being a bit weird, and we had to, yeah. So I just wanted to make sure everyone's on the same page as to who people are. So on the top right, you'll see a profile thing. If you click into your actual profile, it'll show your name there. Yeah, no, I get you're in there. There's your like profile pic and the name associated with it. That's what I'm trying to find. Because I type up Timothy and I don't see anything. Like I get that you're in there. I just want to know what account you're connected to, because on my paying list I don't actually see you there, because these are paid classes. Just wondering, maybe it's like on a different name, maybe a different like parent name that I haven't matched it to. And you're fine, by the way, if you didn't realize that. Like, I understand things will happen. Just wanted to, clarify where we're at. Are you seeing where your profile is? Yeah, I see that screenshot, but it doesn't have your profile in it. What I mean is, if you zoom even further. Oh, okay, that one didn't send. Yeah, that does definitely say your name. Why can't I find you? Better refresh. And then again. Seems like it disappeared. I'm just trying to match it up. What are we doing here? Yeah, that's what I thought.